Welcome to Brain Vision.
Okay, so our first step here is to determine the rate of heat transfer in the steam, okay? So now let's focus on our first step. So first we can set out the energy balance equation here, which is E dot in equal to E dot out. We expand it, we have Q dot plus M dot 1 times H1 is equal to M dot 1 times H2. So if we do some arrangement here, eventually we have Q dot is equal to M1 dot times H2 minus H1. So Q dot here is the rate of heat transfer in the steam, and M dot 1 here is the mass flow rate for the steam. And H2 here is the final enthalpy of the steam, and H1 is the initial enthalpy for the steam. So we know the mass flow rate of the steam is given as 15 pound mass per minute. If we convert it to pound mass per second, it's about 0.25 pound mass per second. So for H1, which is the initial enthalpy, we need to use the interpolation to determine the H1, okay? Because in the table of the superheated water table, there's no corresponding enthalpy at 30 psia, okay? So therefore, we need to pick the range for the 30 psia here. So we know 30 psia is lining between 20 psia and the 40 psia. And so therefore, at 20 psia and 400 degrees Fahrenheit, we found that the corresponding enthalpy is 1239.3 British thermal units per pound mass. And then at 40 psia, 400 degrees Fahrenheit, we have the corresponding enthalpy is 1236.5 British thermal units per pound mass. And the 400 degrees Fahrenheit here, we know is the inlet temperature for the steam, okay? So eventually we can use the interpolation equation here, and then we'll get the initial enthalpy for the steam is about 1237.9 British thermal units per pound mass. And then if we use the superheated water table, so at 25 Cr and 212 degree Fahrenheit, we have the final enthalpy for the steam is 180.21 British thermal units per pound mass. So now we can plug in back to the equation to determine the rate of heat transfer in the steam, which is equal to negative 264.423 British thermal units per second. Okay, which means that the rate of heat transfer in the steam is actually transfer out of the steam since it's negative. Okay, which means that it's losing amount of heat, which is 264.423 British thermal units every second, which makes sense here because if you take a look at the enthalpy here, as you can tell, the final enthalpy is more than the initial enthalpy, which means that the final temperature is less than the initial temperature, okay? So if the steam is losing heat, that means the air is gaining heat, according to energy conservation law, okay? So therefore, we have the rate of heat transfer into the air is equal to negative Q dot, which is equal to 264.423 British thermal units per second. So now let's use the equation to set out with the rate of heat transfer in the air, which is Q dot air is equal to M dot A times Cpa times T2 minus T1. M dot A here is the mass flow rate for the air. We don't know that, but we don't need to know the mass flow rate in this case, okay? Because our goal is to determine the inlet volume flow rates for the air, okay? So let's keep continue. So and Cpa here is the specific heat for the air, and we know T2 is the final temperature, T1 is the initial temperature. So now if we do some arrangement here, we have M dot A is equal to Q dot air over Cpa times T2 minus T1. Remember, the mass flow rate of the air can be expressed as ρ1 times V1 dot. ρ1 is the density of air at the inlets, and V1 dot is the inlet volume flow rate we need to determine, okay? And we know the density can be also expressed as P1 over RT1. So P1 is the inlet pressure of the air, and R is the gas constant of the air. T1 is the inlet temperature of the air, okay? If we do some arrangement here, we'll have the M dot A is equal to P1 times V1 dot over RT1. Okay, so eventually we have P1 times V1 dot over RT1 is equal to Q dot air over Cpa times T2 minus T1. So eventually you have V1 dot, which is the inlet volume flow rate of the air, is equal to Q dot air times RT1 over P1 times Cpa and n times T2 minus T1. So we know the rate of heat transfer into the air, and the gas constant of the air is 0.3704 psia times feet to the power 3 per pound mass times the Rankine. And we know T1, which is 80 degrees Fahrenheit, if you convert it to Rankine, it's about 540 Rankine. And then we know T2 is 130 degrees Fahrenheit. We know P1 is 14.7 psia, and the specific heat for the air is 0.240 British thermal units per pound mass times degree Fahrenheit. So now let's plug in back to the equation to determine the inlet volume flow rate of the air, which is equal to 264.423 British thermal units per pound, not per pound mass, let me see, per second. And then multiply by R, which is 0.3704 psia times V to the power 3 over per pound mass times Rankine. And then multiplied by the inlet temperature, which is, so we use 540 Rankine in this case, okay, because the units of the gas constant is composed with Rankine here, okay, so therefore we need to use the corresponding units, which is Rankine, okay. And then let me see, and then over P1 CPA, which is 14.7 psia multiplied by 0.240 British thermal units per pound mass times degree Fahrenheit, and then multiplied by the changing temperature here, which is T2 minus T1, which is 130 degree Fahrenheit minus 80 degree Fahrenheit. So the reason why we use Fahrenheit in this case, because the specific heat of the air is composed with the units degree Fahrenheit. So therefore we use the corresponding units for the temperature, which is degree Fahrenheit in this case. Okay, so now let's determine the answer. So the inlet volume flow rates for the air is about 300 feet to the power 3 per second. And this is the answer for this question.